name is Grayson Moses, and this is my remote sensing final project. The goal of this project was to build a device that can scan an object on campus into a three-dimensional model. By doing so, each student gains an intimate knowledge of how LiDAR systems work and some of the problems commonly associated with them. For my scan target, I chose a picnic table outside the Agricultural Sciences building. I chose this picnic table because it is large enough to be able to scan at a recognizable resolution, but not too large that I would have to spend a ridiculous amount of time to scan it. There are several other picnic tables on campus just like it, including two others outside the same building, but I chose this one because it is badly warped from the weather and being placed on uneven ground, and I hope that this unique shape would be visible in my 3D model. To create the 3D scan, we first need to understand the science behind it. To collect data of the scanned object, I am using remote sensing, a term which means that I'm gathering information about an object without any physical contact. More specifically, I'm using active remote sensing, which means that the signal I am collecting which gives me information about the object is a signal that I created. In the case of this project, the signal created is laser light, and the sensor that receives the signal is a camera. This signal and sensor combination is a form of LiDAR, which will be explained shortly. The opposite of active remote sensing is passive remote sensing, in which you gather information from signals created by natural phenomena, such as sunlight reflecting. The data collected by the camera is then processed by a computer to give meaning to the data through formulaic calculations. Computer vision refers to the process of using computers to give additional meaning to data acquired in the form of digital images. The key principle of LiDAR is that light, usually in the form of a laser, is emitted towards an object, reflects off the object, and is collected by a sensor. In typical LiDAR instruments, the object's distance is measured by the amount of time it takes for the light to be reflected, as the speed of light is known. However, because the electronics required to measure the time taken for light to reflect off nearby objects are extremely precise and expensive, this project modifies the principle. To demonstrate, consider a cube in a room. A horizontal line is projected onto the cube with the use of a laser. If you look at the cube from the same height that the line is being projected from, the line will appear horizontal to the viewer because every point on the cube that the laser hits is at the same height as the viewer. However, if you view the laser from another view, in this case above and to the right, the laser no longer appears horizontal. Every point on the line is still at the same height in reality, but to the viewer, the points of the laser on the side of the cube appear higher because they are further away. This is the principle of parallax. If you know the distance between the line projector and the viewpoint, you can do some math to figure out how much higher the line will appear. Here is my device that I created for data collection. On the top is a Raspberry Pi computer with a camera mounted on the front, and on the bottom is an Arduino, which communicates with an accelerometer on the front and provides 5-volt power to the laser, which is on a lunch break right now. The Arduino is connected by USB to the Raspberry Pi, which powers it and allows the transfer of data, and the Raspberry Pi is in turn powered by a portable battery. I chose to make my electronics mount out of Lego because it allowed me to make a more customized and modular design, and it is easy to take apart and set up in the field. The key feature of the mount is a gear that can rotate the whole mount, which is useful for data collection and will be explained later. An angled piece allows me to calibrate the accelerometer to vertical and 45-degree angles, and a latch on the top allows the removal of the Raspberry Pi. The entire mount can be easily detached from the tripod with the removal of 2 pins. The Lego mount snaps easily into the camera tripod. In order to process the data with the use of computer vision, the computer needs to know which areas of the photos to care about. For this project, the computer is only concerned with pixels that are returns from the laser. To ensure that the computer only looks at these pixels, a filter is created. To do this, I took pictures of a single-point laser and experimentally found a range of hue, saturation, and brightness values that includes all laser pixels and no non-laser pixels. Then, I placed the camera and laser 12 inches apart and projected the laser onto a piece of paper that I moved towards the camera in 6-inch increments. I plotted the position of the laser points versus distance from the camera against a set of theoretical values to see the principle of parallax in action and to ensure that my hardware was functional. However, it's clear from the mismatch between the two plots that calibration would be necessary to properly process any future data I collect. To calibrate the image, I used my newly built device to shine the line laser on a blank wall in increments of 6 inches from 0 to 10 feet, an image is shown here. The location of the laser line in the image was again plotted against theoretical values, and two variables representing alignment errors were manually changed until my theoretical data matched my collected data. With my camera and laser firmly secured to my device, I could be confident that these two error variables would remain constant for any objects within 10 feet of my device in the future. Now that my device was calibrated, I tested its capabilities by scanning a chair in my room. I ran into a snag because I included a number in the folder name containing the data, which resulted in the 3D points not being plotted properly. But after I fixed this issue, I had data that was recognizable as my chair, although with lots of noise. So here's what it looks like to be taking data. Here you can see me tilting the laser up and down using the tripod. When it's in position, I go to my laptop, which is connected to the Raspberry Pi via VNC remote desktop, and manually input the angle from the accelerometer reading shown on the screen. After this, the view of the camera is shown and the picture can be taken. This footage was taken during the day just to show the setup of the instrument. All data had to be taken after sunset. Here's what it actually looks like to be taking data. I'm out here at night so that the laser's light is visible and can be distinguished from its surroundings. Here you can see the laser shining on the bench. As before, the accelerometer displays the angle which is manually input. The photo is shown with the angle displayed, and then the M key is pressed to save the photo. After taking a photo, I now rotate the mount upwards using the gear on the back, putting the laser in a new position. Going back to the computer, I put in the angle and save the photo, then repeat the process again. At first, I had difficulty getting good images. When the sun was out, the environment was too bright to see the laser, but if it was too late at night, there was not enough light entering the camera for it to see much at all. Here you can see that as time went on, the laser appeared dimmer and dimmer. This made it hard for me to filter my data for the laser line. Fortunately, another student found that you can decrease the shutter speed and frame rate of the camera to put it in a long exposure mode, making lights appear brighter. This instantly fixed my data, and I got some great photographs. I ended up taking 6 scans of the table. 4 scans were at a 45-degree angle to the 4 sides of the table. 1 scanned the side, 1 scanned the back, and 2 scanned the front of the table at different distances so that the A-frame of the table could be seen in the scan. To process my data, I created a new script based off a script given to us by the professor to choose the HSV values for the filter. Because I had multiple sets of scans in different folders, the program first asks for the name of the folder to parse. It then opens each image and allows the user to pick an individual HSV range for each image. When the user is satisfied, they press M to save the filtered photo and move to the next photo. The filtered images are then put in a second Python program that converts each of the filtered points into a 3D point. The 2 error variables previously determined are used here to correct the data. Here I've changed the default value of the distance between camera and laser from 12 inches, as LEGO is on a metric scale and I chose to make them slightly further apart. The program parses through all the images in the folder specified by the user, picking out each point created by a laser return and using its horizontal position in the image to determine how far away from the camera it is. The horizontal position is used because the camera was used sideways for data collection. Each point is written to a text file as a list of 3 points representing its X, Y, and Z distance from the camera, and it shows a plot of the points when it's done. As you can see here, despite anyone's best efforts to filter the laser and only the laser, single pixel noise will still end up getting through. Clearly, the giant mass of points that don't match any table feature are not appropriate to keep in my point cloud. So the first thing I do in MATLAB is to delete those points and make a new text file without them. Now that the far-off points are removed, it's much easier to see the geometry of the scan. With erroneous points removed, all that remains is to stitch the scans together. I did this manually by using one scan, the close-up front scan, as a reference for everything else. I would display both point clouds on a graph at the same time, and guess how the second point cloud needed to be rotated and translated in order to match up. I moved point clouds using affine transformation matrices, which is a matrix that when multiplied by the original matrix of points moves the points by a desired amount. Once it lines up, I can move on to adding the next set of data. Here's my final point cloud with the most obvious erroneous points removed. It's crude, but definitely recognizable as a picnic table. The tabletop and both benches are clearly visible. The A-frame of the table is certainly visible to some extent, but suffers from more noise than other areas. You can also see the distinctive bend in the table and the fact that it's on uneven ground, which I set out to achieve from the beginning. To turn the points into a 3D object, I used a program called MeshLab. After importing my points, I first used a tool to compute the normals to each point. This means the program places a vector on each point, pointing in the direction that the program guesses would be perpendicular to the surface of the 3D object. To help the program, I set the viewpoint as a point high above the middle of the object so that most of the vectors would point upwards. Next, I used a tool called Poisson Surface Reconstruction to generate a surface from the points. There are settings you can change for this tool, but I did not find that my mesh was improved by making any changes to them. As you can see, the program basically lays a sheet over the entire mesh to create the surface. However, the program does not know where to stop the sheet, so I need to cut the excess off with another tool that removes highlighted surface sections. Trimming the edges was easy, but trimming around the benches was a pain in the butt. Here's what my finished mesh looks like. I don't think MeshLab does a very good job for the purposes of this project. However, my result is more or less recognizable as a picnic bench. All detail is lost on the inside and for the A-frame, and there's lots of lumpiness and holes. However, if you turn off the view of the surface, the shape of the table is more clearly visible from just the point cloud. Thank you to Dr. Mitchell for creating and teaching this class. It's a really cool project, and I had a lot of fun with it. I appreciated all the opportunities for creativity, and I learned a lot from it. Also, thanks to the classmates who created solutions for the class and for everyone who helped troubleshoot.